So I briefly mentioned this at the end of the illustration in our 3 example, but one of the key ideas in linear algebra is to study the set of vectors that can be written as a linear combination of a fixed set of vectors, or in other words, the spanning set. So here's that more formal definition of the span. So if vectors v sub 1 through v sub p are in Rn, then the set of all linear combinations of these vectors is denoted by the span of vectors v sub 1 all the way to v sub p. And this is called the subset of Rn spanned by vectors v sub 1 through v sub p. This is the subset of Rn spanned or generated by the vectors v sub 1 through v sub p. So in other words, the span is the collection of all possible linear combinations of the vectors. So we have the span of this set of vectors v sub 1 through v sub p is the collection of all possible linear combinations. All possible linear combinations of the vectors v sub 1 through v sub p. So in other words, the span of vectors v sub 1 through v sub p is the collection of all linear combinations of the vectors that can be written in the form c sub 1 times vector v sub 1 plus c sub 2 times vector v sub 2 plus all the way up to c sub p times vector v sub p. And this, of course, is such that c sub 1 all the way up to c sub p are the weights, or the scalars, or the coefficients. So the span of a set of vectors is the collection of all possible linear combinations of those vectors, such that we can write them in this form. So keeping this definition in mind, asking whether a vector, say vector b, is in the span of a set of vectors amounts to asking one of 3 possible equivalent things. So the first one is, does the vector equation have a solution? So if you say, is vector b in the span of the set of vectors v sub 1 through v sub p, what you're asking is, does that vector equation x sub 1 times vector v sub 1 all the way up to x sub p times vector v sub p equal vector b? Is there a solution to the vector equation? So keeping this in mind, an equivalent way to ask if vector b is in the span amounts to asking, does the equivalent augmented matrix have a solution? So does the augmented matrix, again, have a solution? And we know that this is an equivalent way to ask because the vector equation is equivalent to the augmented matrix, vector v sub 1, v sub 2, all the way up to v sub p. There's your coefficient matrix being augmented with vector b. Another way to ask this same question is, does the matrix equation have a solution? So does the matrix equation have a solution? So in other words, does that matrix equation, matrix A times vector X, equal vector B? And this, of course, is such that matrix A is defined by the column vectors v sub 1, v sub 2, all the way to vector v sub p. So if the vector equation has a solution, or the equivalent augmented matrix has a solution, or if the equivalent matrix equation has a solution, then yes, vector b is in the span of that set of vectors. So here is a little strategy to check if vector B is in the span of a set of vectors. So keeping those three equivalent forms in mind, the first thing that we want to do is row reduce the augmented matrix. So I'll abbreviate the augmented matrix. So if you're only given that set of vectors, you want to put those vectors into your augmented matrix and start row reduction. Now, we don't have to go all the way. If amongst our row reduction, we are able to attain an equivalent matrix in echelon form, then the system is consistent, and thus a solution exists. So if we can attain echelon form, then we know that a solution exists, or then the system is consistent and a solution exists. And at least one solution exists. So this tells us, in other words, that vector B can be written as a linear combination of the columns of matrix A. And let's give ourselves a little more room. So what is this telling us? This is telling us that then yes, then vector B can be written as a linear combination of the columns of the matrix. Or simply a linear combination of the vectors v sub 1 through v sub p. And since the span is the collection of all possible linear combinations of these vectors, then we can officially conclude that yes, vector B is in the span of that set of vectors, v sub 1 through v sub p. So we will row reduce the augmented matrix. If we can attain echelon form, then the system is consistent and must therefore have at least one solution. So if at least one solution exists, then vector B can be written as a linear combination of those vectors, and therefore vector B is in the span of the set of vectors. So let's go ahead now and take this strategy and apply it to some examples.